So at the end we have the traditional how to do things in our video, where I'm going to actually go through the most of the examples I showed you in the lecture, and it will be mostly these iris examples. Okay. So first of all, let me load the MDA tools library. We don't need MDA tools library for the methods, but MDA tools has a nice has some nice plotting functions, plotting possibilities that I will employ. Okay. As I said, the R has data set iris built in, so you simply say data iris here. Then you can see this is the iris data set, and then if you want you can see the values. If you just, for example, write head iris, then you can see this is the head of iris, right? So you can see sepal length, sepal width, petal length, and petal width, and then the species. Let me split this data set into, first of all, I will keep the measurement separately from the class names, and then I will also make the calibration in the test set. Okay, so I know that the first four columns is where I have the measurement, so I will simply subset the iris dataset, taking first four to as a x, and then the classes will be saved to a variable c. It's a column number 5. And then I need to make a test set, and I will simply take every fifth measurement. That will give me exactly 10 measurements for every class, evenly distributed. I know that the rows already shuffled. So first of all, I create a vector with indices. For the rows I want to take as a test set, I will simply say it's a sequence from 1 to 105 and 50, and then by 5, right? So it will take the first, the 6th, the 11th. You can see all the indices here. Then I simply say for the calibration set, we take all rows from X, but not the ones that are in this index, right? So I use minus here, and I do the same for the classes, C, and then minus T dot end. So I don't take the ones that I want to use only for test set. Then for test set, I take exactly these ones, right? So this is how to do it. And then I remove minus here. So if I run it now, you can see that, let me just run it from scratch. So you can see that in XC I have 120 observations, and then in XT I have 30, and then you can see it's the same for the CC and CT. Okay, so now I'm ready, and then the first thing I want to do is to show you how to do k-means clustering. Well, first of all, I mean, for k-means you don't need any packages. It's again built into R, the basic R, and then you just simply say results equal to k-means, and then you remember it's unsupervised method, so you don't have to provide any classes, just the measurements. So it will be XC, the calibration set. And then if you provide XC, it will take all columns into account. Let me take only column number 3 and 5. It's a petal width and petal length. I know in advance this is the columns that gives the best separation actually. So I will just make it this little trick. The second argument is how many centers I want to use, how many clusters. I need 3 clusters. And then you can see maximum number of iterations, it's 10. Let me use, for example, 20 iterations. So I say the iter max equal to 20. Now if I run this, you can see I get a list with results, and if I open this list you can see the first element, it's cluster, and it's exactly the names, the numbers of clusters that I want. Then I have centers, I can show where the centers are, and then some other statistics. Okay. If I want to visualize this, I can, first of all, I can make a plot. For example, I can say MDA plot XC, right? And then this column number 3 and 4. Then I can use this nice feature of MDA plot C group, and then I will use res cluster to group by the clusters, the cluster we found, right? So let me just make it bigger, the image bigger. Here we go. So you can see this is the clusters. Of course, it takes the number of randomly, so this is cluster 1 in this case, this is cluster 2, and this is cluster 3, right? I can also show the same data but cluster it by the correct classes, right? Let me just combine this in 2 together. Par mf row equal to, let's say, 1 and 2. So you can see that actually if I make it a bit wider, you can see, for example, this is perfectly clustered. Then you can see, for example, these 2 points, they are from this cluster, that's correct. But these 2 points, you can see they should be from this cluster, but in fact they are vice versa. These 2 points should be from the green cluster, but in fact you can see they were recognized as a cluster of 3, right? You can see some here on the overlapping area we have some issues with clustering, right? But once again, of course, it's very rarely when you have this the data truth, the ground truth. You never know. When you use clustering, you usually don't know you don't have the training set, right? You don't know which cluster or which group or which class your data came from. Okay. And then I mentioned a little bit hierarchical clustering. Actually, R also has a built-in function to hierarchical clustering, and this is how it works. I will show you hierarchical clustering. Show you quickly. First of all, hierarchical clustering, you remember it's any clustering, it's measured on the similarity. Hierarchical, something like this. It's based on similarity. And I need to compute this similarity matrix first of all. Luckily in R there is a function for that, and it computes similarity matrix simply by measuring distances between all points. Okay, so it takes the first point and measure distance with the other. For example, 119, then it takes the second point and measure distance with the rest 119, and so on and so forth. By default, it's Euclidean distance. You can see this is function dist, but you can change this method. You can use other distances. You can try it yourself. And then look, I just apply it to my XC data. And then, for example, let me use XT, just because XT has only 30 values, so it will be easier to visualize. So if I compute it for XT, you can see this is the matrix. You can see, for example, let me just go up from the start. Here we go. So this is the distance between observation 1 and 6. This is the distance, for example, between observation 11 and 1, and this is the distance between observation 11 and 6, and so on and so forth. So you can see some of the distances can be pretty large, some of the distances are small, and this is the ground for the clustering. Okay. Now we're ready to do the clustering. We simply say make a hierarchical clustering. Again, there are many different methods to do the hierarchical clustering. I will use the default one, but you can later look at help for this H-class to find which methods actually exist. So I do that, and then I can simply plot the result like this. So you can see this is a dendrogram. Let me just get back to a plot with one figure, like this. So you can see this is a dendrogram, so this is a clustering. And these are numbers of objects. Luckily, I can also define labels, so I can simply use the classes I know. It's CT for the labels, and now you can see that we have a pretty good clustering, right? So you can see this one is one cluster, one big cluster, and then the smaller ones, and then you can see that all clusters here in this branch of our tree, it's all Virginica, right? Then we have another branch, this one, a big branch as well, and this is Setosa. And then we have the third branch, and this is actually versicolor. So you can see actually the clustering was quite correct. Yeah. Again, it's a bit strange to say clustering was correct, because strictly speaking, when we do clustering, we have no idea what class every measurement is from. But in this case, we have this information, and therefore I can actually visualize it. Okay. So that's the clustering. Now let's talk about the k-nearest neighbors. K-nearest neighbors. And for k-nearest neighbors, you need to load the package library class. It's called class. Remember, if you don't have this package installed, remember to install this package first. Run install packages class, or just click here, packages, install. Then as soon as you install it, come back and then follow me. So I have it installed. I simply load it, and then I can make this classification. So I say the predicted class. It returns just labels for predicted class. Then KNN. And then you remember there are three things. First of all, it's the calibration set. It's a test set. Then labels for the calibration set. And then how many nearest neighbors I should take into account. Yeah? So if I run it and then look at the CP, you can see that this is the result. So it tells me that the first measurement is Setosa, was classified as Setosa. Second measurement was classified as Setosa, and so on. Okay. Because I know also, for example, I can combine this together. I know the real class, it's CT, right? So I can see that, for example, do I have any misclassification or not? So you can see this one, right? So, I mean, it was classified as class number 3, but the real class is number 2. I have at least one misclassified value, right? Actually, I can make very quickly, I can make this confusion table. I can write just table CPCT, and then you can see the confusion table, right? So you can see Setosa. this is CT, so this is the real values, and this is what the model says, right? So maybe if I want to make it correct confusion table, I should do it other way around. So this one. So this is the reality, and this is what model says, right? For example, setosa, it was recognized as setosa, all 10 values, right? Then versicolor, you can see 9 was recognized as versicolor and 1 was recognized as virginica, right? And then you can see virginica, all 10 were recognized as virginica. So for the test set, we have only one misclassified object, so the accuracy is 29/30. Yeah. And then I can also visualize the results. For example, I can make a plot. Let me again use two plots. So I show the reality and the classification results. First of all, I'll show you the reality. MD plot x. Let me use, although for k and n I use all 4 variables, let me use the third and the fourth variable for visualization. Okay, it's CT. So let me just do it again. XT. I forgot to say XT. So this is the reality. Okay, so this is my test set, 10 values for each, 10 measurements for each, and this is the real class membrane, right? And then I can do the same and colorize by the predicted class. And then you can see where the wrong value is. It's this one, right? So you can see that, oh, it's this one. So you can see that in reality it should be green, but it was classified as red, as a virginica. Yeah. I can actually make a nice trick here. I can say points, for example, xt, and then I can say which ones. Only where CT is not equal to CP. So I will show only points where CT and CP is the predicted value for class and the real value for class is not the same. And then I can say use the same columns. Let's say the point character is 1. Point character is 1. Then let me make it bigger. Okay. Then you will clearly see where actually you can see a little circle around. So it's exactly this point where we have a misclassified object. Yes, so that's the k nearest neighbors, and then finally neighbors. Yeah, and then finally the confidence ellipses. Confidence ellipse, right? So in this case, first of all, let me make a plot, and I will use again a big one. So I will get back to 1 row and 1 column in my figure, and then I make a plot, MDA plot. X, let me use again 3 and 4 columns, and then C group equal to, in this case I need to use a calibration set, so let me use calibration set here, and then CC, right? Then you can see that you can see a little like a white space here, because actually CC is a factor. We know that this is a factor. You can see it has levels, right? So R knows it's a factor, right? And in MDA tools, there is a nice feature. So if I save results of this plot to a variable p, then I can make a confidence ellipse around every group, because I know which points are from which group. So this is how to do it. I use plot confidence ellipse and then p. By default, it will be 95% confidence ellipse, and I can change it. I will show you in a minute. So you can see the confidence ellipses. For example, in this case, you can see that many setosa are out, like 4 are out, right? We have 1 out here, and then we have 1 out here. I can change the confidence, level. For example, I can say 99, and then it will make the ellipses bigger, right? So now you can see I have only 1 out here, and then none here, and then none here. Yeah. And then what I can do, for example, I can also show the, let me add the test set, MDA plot. XT, columns number 3 and 4. And then let me, for example, first of all, let me use also coloring. And then let me use PCH equal to, let me see, 3, for example. And then I will say show axis equal to false, because I don't want to make a new plot. I want to add these points to the plot I made before. Okay. Now you will be able to see the test set as plus. And then you can see, for example, in this case, all pluses will be classified correctly. In this case, you can see we don't have any green pluses outside, right, as far as I can see. So all pluses will be classified correctly, but we will have some false positives here. You can see some green points inside the ellipse for the red points inside the green ellipse, and also we have a lot of green points inside the red ellipse, of course. And then if I change the confidence level, you can see that, of course, it will increase the number of false negatives, Now I have a lot of, for example, red points outside, but the number of green points inside the red circle, the red ellipse, will be also smaller, and then the same for the green, right? So when we change the confidence level, in this case, we of course change the number of false negatives, but we also change the number of false positives, right? So that's actually it. Now you know how to run these simple classification methods, and then next learning sequence is about projection-based methods.